Welcome to this explainer. Okay, picture this. You've just built this absolutely incredible machine learning model. It's working perfectly on your laptop. You're feeling great. But then you put it out into the real world and it just completely crashes and burns. Sound familiar? Yeah, we've all been there. Today, we're undertaking a massive shift in how we actually think about machine learning. Look, we all start out building models in notebooks, right? They're interactive, they're fun, they're fantastic for exploration. But here's the harsh reality. A fragile model sitting in a Jupyter notebook is entirely different from a robust, living, breathing production system. So today we're going to bridge that gap. We're going to learn exactly how to upgrade our workflows from top to bottom. Let's get into it.
Okay, let's dive right into this. The absolute core mantra that's going to drive everything we talk about today is actually really simple. A model is not a product. A pipeline is. Seriously, burn that into your brain. A standalone machine learning model is really just a mathematical equation sitting on your hard drive. It doesn't actually do anything useful on its own. To make it a reliable product, you need the entire sequence. I'm talking about everything from raw data ingestion all the way to a deployed prediction. And absolutely every single step of that journey must be completely reproducible. No exceptions. Let me paint a picture that might be just a little uncomfortably familiar. You've got your notebook open, you load up some data, you fill in those missing values with the median, you scale the features, train the model, print the accuracy, and boom, it works. You're getting great numbers. So you ship it. But fast forward a month later, someone retrains the model and gets entirely different results. Or worse, it just outright fails in production. Why does this happen? Well, maybe that median you used was computed on the full data set, meaning test data sneakily leaked right into your training. Or maybe your scaling parameters weren't saved, so your live inference is using completely different statistics. Or hey, maybe a categorical column just gained a brand new value in production, like a new city name that your encoder has literally never seen before. Look, these aren't just hypothetical nightmares. These are the actual most common reasons machine learning systems fail in the real world.
Section 1. Stopping the silent killer.
Now, what's really interesting here is looking at the main culprit that silently destroys our models. It's called data leakage. It's a silent killer. Data leakage happens when information from your test set or future data somehow contaminates your training process. Think about it. If your scaler sees the test data before you split it, the mean and standard deviation now include those test samples. So your model essentially gets to peek at the answer key. It artificially inflates your accuracy estimates. You think you have a game-changing model, but honestly, it's a total illusion. Contrast that with the correct approach. An automated pipeline strictly handles the fitting on the training data only. The test data remains totally unseen, exactly as it should be.
Section 2, enter the ML pipeline.
So here's the million-dollar question. How do we enforce this correct behavior every single time without relying on our own error-prone human memory? Well, we need a pipeline. Think of a pipeline as an impenetrable assembly line for your data. Literally, it is an ordered sequence of data transformations followed by a model at the very end. Each step neatly takes the output of the previous step as its input. Now, here's the magic. The entire pipeline is fitted just once on the training data. Then, at inference time, that exact same fitted pipeline transforms your new data and produces predictions. Data goes in, predictions come out safely, and the whole object can be serialized and deployed as one single solid artifact. Beautiful, right?
And this brilliantly illustrates the landscape we're working in. Because to build these pipelines, you're going to hear a lot of jargon, so let's translate real quick. A column transformer? That's what you use when real-world datasets have a messy mix of numeric and categorical columns that need different types of pre-processing. It stops production crashes by handling unknown categories gracefully. Then we have MLflow. That's an open-source platform for experiment tracking, basically logging all your parameters, metrics, and code versions so you don't lose your mind. DBC is often called the Git for data. It stores huge data files remotely but keeps track of their versions. And finally, a model registry. That's essentially just a catalog that tracks your model versions with handy stage labels like staging or production. Let's actually pop the hood and look at the mechanics of how a tool like scikit-learn's pipeline works. When you call .fit on your training data, the scaler calls fit_transform, and then the model fits on that newly scaled data. Pretty straightforward. But when you call .predict on your test data, the scaler strictly calls transform, not fit_transform, before the model predicts. Do you see what happens there? The scaler never ever sees the test data during fitting, and that is exactly the whole point. Plus, if you're using cross-validation, the pipeline is applied perfectly per fold, preventing any of that subtle leakage across your validation sets. It handles the heavy lifting for you. Section 3, tracking and versioning everything. So imagine you run 50 different experiments trying to find the absolute best model. How on earth do you remember exactly what you did for experiment number 17? You don't. Unless you have a system. A truly reproducible experiment requires 4 non-negotiable pillars. First up, fixed random seeds across your entire framework, whether that's NumPy, Torch, or sklearn, so your randomness is actually, well, predictable. Second, pinned dependencies. You need a requirements.txt or a poetry lock file so your environment doesn't randomly shift underneath you. Third, versioned data. And fourth, configuration files. You absolutely cannot have hard-coded hyperparameters scattered all throughout your code like a scavenger hunt. They must be centralized in a config file. So the crucial point is this. If you are missing even one of these pillars, you do not have true reproducibility. Period.
Now, I really want to pause on that third pillar for a second, versioning data. We all know Git, right? It's fantastic for versioning code. But let's be honest, it completely chokes on large data files. And this is exactly where DVC, or Data Version Control, swoops in to save the day. DVC stores the actual heavy gigabyte-sized data files in remote storage, like an AWS S3 bucket or Google Cloud Storage. But what it keeps in Git is just a tiny, lightweight text file containing a hash. It is a remarkably clever trick. What this means is that whenever you check out a specific Git commit, DVC automatically restores the exact data that was paired with that code. Every single commit pins both the logic and the data perfectly together. It's a real game changer.
Section 4, Notebook to Production Pipeline. Let's move to the actual blueprint and see how this builds into a robust production system. Taking that messy notebook and transforming it, chronologically, you're going to start with step 1, notebook exploration. This is great for testing feature ideas quickly, but then, and this is key, you must extract those functions into dedicated modules. Step 2 is building and chaining those transformations into a formal pipeline object like we talked about. Step 3, move your hyperparameters to a config file and add experiment tracking like MLflow. Step 4 is absolutely crucial, data validation. You have got to check schemas and missing value patterns before you ever let new data touch your model. Step 5 is writing unit tests for your transformers to make sure they do what you think they do. And finally, step 6 is deployment. This is where you serialize that single pipeline object, wrap it up in an API, and containerize the whole shebang.
Even with this blueprint, teams still stumble. It happens. But the most massive pitfall you need to avoid is doing feature engineering outside the pipeline. Why is this so bad? Because it leads to what's called training serving skew. That basically means your model ends up seeing slightly differently processed data in production than it did during training. And that causes silent errors, which are the absolute worst kind. The fix is remarkably simple, though. Put all your transforms inside the pipeline object itself. Just bake it right in. Another super common mistake is hard-coding column names. If a database schema changes, your code breaks instantly. So always pull your column name lists straight from your configuration file. Wow, okay, we've covered a lot of ground today. We went from the silent killer of data leakage to the inner mechanics of scikit-learn, all the way to versioning gigabytes of data with DVC. But honestly, all of this information boils down to one critical look in the mirror for your own projects. So I'll leave you with this question. Is your machine learning system a fully reproducible, robust pipeline, or is it just a fragile notebook waiting to break? It's time to start extracting those functions and building your pipeline today. Thanks for joining me on this explainer, and I'll catch you next time.